Welcome to White Space. How many galaxies does the universe actually hold? Put this on in the background. Close your eyes if you want, and let the story carry you. Let's begin. There are things we take for granted: the ground beneath our feet, the sky above our heads, stars scattered across the night sky like salt on black glass. We are accustomed to thinking they simply exist, hanging up there in the heights, gazing down at us with cold indifference. But if one rises above the atmosphere, ventures beyond the solar system, leaves the Orion arm, and looks at our Milky Way from the outside, something entirely different is revealed. Not chaos, not emptiness, structure, a grand architecture worked out to a billion details, in which our galaxy is merely one element, one among billions of similar stellar islands scattered across a space that has no end. We live in an era when humanity has for the first time obtained instruments powerful enough not merely to look at these islands, but to understand their nature. Before we saw hazy patches and did not know what lay behind them. Today we know each such patch is an entire world, or several worlds. A galaxy is not simply a collection of stars. It is a living system with its own history, its own character, its own future, and its own death. How many galaxies there are in the universe is a question without a definitive answer. Several decades ago, 100 billion was the figure given. Then a recount pushed the number to 2 trillion. Now the estimates have been revised again, and astronomers prefer cautious formulations. Hundreds of billions, possibly more. This is difficult even to imagine. If one were to take each galaxy as a separate country and allot it 1 second of attention, the enumeration alone would take more than 6,000 years. Without sleep, without stopping, with the naked eye we can see only 4 of them. In the northern hemisphere, the hazy patch of the Andromeda galaxy and the barely discernible object of the Triangulum galaxy. In the southern, the large and small Magellanic clouds. Everything else is the exclusive province of telescopes. But even what we see through a telescope does not fully correspond to what is actually there. Galaxies have no sharp boundaries. One cannot draw a line and say, here it ends and here intergalactic space begins. This is not a planet with a solid surface or a cloud with a visible outline. The boundary of a galaxy depends on the wavelength range in which one observes it. In visible light, one thing. In the radio range, by the distribution of neutral hydrogen, something entirely different, and often twice as large. Let us begin with the fundamental question. What is a galaxy and what is it made of? Imagine a city, not a small provincial town with a park and a single traffic light, but a metropolis with districts, underground thoroughfares, business centers, outskirts, and suburbs. A galaxy is organized in a similar way, except that instead of neighborhoods, there are stellar components, each fulfilling its own role. At the very center, the nucleus. This is the densest and most energetically intense part of the galaxy. It is here, in the view of most astronomers, that the supermassive black hole lurks. In active galaxies, this nucleus shines brighter than the rest of the galaxy combined, ejecting powerful jets of charged particles over distances comparable to the size of the galaxy itself. In such cases, one speaks of an active galactic nucleus. In our Milky Way, the black hole is considerably more modest, a mass of about 4 million solar masses, and it behaves quietly, barely announcing its presence. But astronomers know this is a temporary lull. Around the nucleus lies the bulge, a spherical or slightly flattened thickening composed predominantly of old stars. Red and orange giants that have spent most of their fuel? The bulge is the historical archive of the galaxy. It is here that the earliest generations of stars are preserved, formed at the very dawn of galactic evolution. In lenticular galaxies, the bulge is generally larger relative to the disk diameter than in spiral galaxies. Beyond the bulge stretches the disk It concentrates the bulk of the visible matter in spiral galaxies. Everything here is different. The disk is rich in interstellar gas and dust. Young blue stars burn here, and a continuous cycle of births and deaths takes place. The spiral arms are not rigid structures, but density waves slowly rolling through the disk and triggering bursts of star formation. Molecular clouds contract, new stars ignite. The most massive among them quickly live out their lives and explode as supernovae, enriching the surrounding space with heavy elements. The stellar nurseries are located precisely in the arms. The Orion Nebula, visible to the naked eye as a hazy spot in the sword of the same constellation, is one of the nearest regions of active star formation to us. Through a telescope, one can make out the complex structure of this nebula, illuminated by the young hot stars of the trapezium, a youthful star cluster within it. Young, massive stars in the arms live briefly from a few to a few tens of millions of years. Stars such as blue supergiants burn rapidly and die in spectacular explosions. Behind them remain nebulae of ejected material and super-death remnants, neutron stars or black holes. The longest-lived inhabitants of the disk are the red dwarfs, which consume their hydrogen fuel frugally and are capable of burning for trillions of years. Not one of them has yet had time to go out since the Big Bang. Dispersed star clusters are also born in the galaxy's arms. Clusters such as the Pleiades or Hyades in the constellation Taurus contain several hundred, sometimes several thousand stars of common origin, bound by weak gravity. Over time they disperse. Interactions with more massive objects gradually break the gravitational bonds. Our Sun most likely was also born in such a cluster, which no longer exists. There is yet another component of the galaxy, polar rings. This is a rare phenomenon, an outer ring of gas and stars rotating perpendicular to the main disk. Such structures are thought to arise from the gravitational interaction of two galaxies. The galaxy NGC 4650 Ab in the constellation Centaurus is one of the most studied examples. Around the disk spreads the halo, a spherical region almost devoid of interstellar gas, populated by old stars and globular clusters. Globular clusters are dense families of hundreds of thousands to millions of stars bound by a single gravitational force. They are incredibly old. The age of many approaches the age of the universe itself. Unlike dispersed clusters, globular clusters do not scatter. Gravity holds them firmly. The Milky Way contains about 200 globular clusters. It is precisely from their composition that scientists reconstruct the chemical history of the galaxy at its earliest stages. Now, on the diversity of forms, if one were to begin a journey through the universe, the first thing to strike would be how unlike one another galaxies are. Some are wound into elegant spirals with bluish arms. Others are giant luminous spheroids with no hint of structure. Still others are ragged and chaotic, like debris after a collision. Elliptical galaxies constitute approximately a quarter of all galaxies with high luminosity, no arms, no active star formation. All the gas was long since spent or expelled, and now old stars reign here, red and yellow. The color of such galaxies is warm, amber. The largest known galaxies belong precisely to this type. Mitsibim in the constellation Virgo is a supergiant elliptical galaxy with a black hole at its center of 6.5 billion solar masses. This was the first black hole to be photographed in 2019 as part of the Event Horizon Telescope project. Spiral galaxies are the most common among bright galaxies. They make up more than half of all known galaxies. Star formation continues in their disks. The arms glow blue. The central bulge radiates the warm yellow light of older stars. Many spiral galaxies have a bar, an elongated dense formation passing through the center and serving as the main channel for delivering gas to the nucleus. Our Milky Way belongs to type SBC, a spiral galaxy with a well-developed bar and widely opened arms. Lenticular galaxies occupy an intermediate position between spirals and ellipticals. They have a disk and a bulge, but no pronounced spiral arms. there is little gas, star formation has practically ceased. A good example is the galaxy M102 in the constellation Draco. Irregular galaxies are a special category. Their shape defies standard classification. Most of them are the result of gravitational interaction, the collision of two systems, or the close passage of a neighboring galaxy. The Large and Small Magellanic Clouds are the nearest examples, visible to the naked eye from the southern hemisphere. They show signs of interaction with our galaxy, deformed structure and streams of neutral hydrogen between them and the Milky Way. Their gravity, in turn, has deformed the outer part of our own galaxy's disk. Such are the complex cosmic relationships. Among the irregulars, dwarf irregular galaxies stand apart. They contain few heavy elements and abundant interstellar gas. In composition, they resemble protogalaxies of the early universe. Studying such objects is like reading the first pages of a book on the origin of galaxies. Those galaxies that do not fit into any category are called peculiar. Their distinctive features are the consequence of gravitational interactions, mergers, and matter ejections. Each of them is a story unto itself. Now, let us leave our galaxy and travel further. Our Milky Way belongs to the local group, a family of about 50 galaxies scattered across a volume some 3 million light-years in diameter. The nearest galaxy to us is a dwarf system in the constellation Canis Major, 25,000 light-years from our solar system. It is currently being actively absorbed by the Milky Way. In this process, a ring-shaped stellar filament has formed, wound 3 times around our galaxy. This is presumably a tidal stellar stream drawn from the dwarf galaxy itself. A little farther, the Large and Small Magellanic Clouds, at 160 and 200,000 light-years respectively, despite their proximity, detailed study of them became possible only in the last century. The Large Magellanic Cloud in the constellation Dorado is the 4th largest galaxy in the local group, with a radius of about 14,000 light-years. The Triangulum Galaxy, M33, the nearest large spiral galaxy without a bar, in the constellation of the same name. It contains about 40 billion stars, considerably fewer than the 400 billion of our Milky Way and the trillion of Andromeda. It is moving in the direction of Andromeda. The gravity of the latter has already drawn some stars from Triangulum, and the stellar bridge has stretched between the two galaxies. Andromeda, or M31, the dominant giant of the local group, located 2.5 million light-years from us. It surpasses the Milky Way by 1.5 times in mass and contains about 1 trillion stars. It is with Andromeda that our galaxy will meet in several billion years. This collision will unfold over hundreds of millions of years and conclude in a merger into a single elliptical galaxy. No catastrophe for the stars. The distances between them are so vast that direct collisions will be almost non-existent. But the interstellar medium will flare up with a new wave of star formation. And from the chaos of 2 spiral galaxies, something fundamentally new will be born. Beyond the local group, space expands rapidly. 6 million light-years away, the Sculptor group, the nearest cluster of galaxies to us. Among them, NGC 300 stands out, a spiral galaxy that turned out to be significantly larger than thought. An extensive, sparse outer disk of old stars was discovered, twice exceeding the visible dimensions. The size of this galaxy thus proved to be 47,000 light-years, and we thought we knew it well. Farther still, the galaxy Centaurus A, NGC 5128, the nearest lenticular galaxy with a polar ring to us in the constellation Centaurus. In the optical range, a symmetric spheroid crossed by a dark dust lane. In the radio range, something entirely different. From its center, 2 colossal jets burst out, extending millions of light-years in either direction. These are the traces of the activity of the supermassive black hole in its nucleus, one of the most active in our cosmic neighborhood. The Searchiness galaxy, with its outflows of hot gas from the central regions, the Maffei 2 galaxies behind the dust veil of Cassiopeia, NGC 55 at the edge of the constellation Sculptor, each of these objects adds a new detail to the overall picture of our galactic neighborhood. The farther we look, the more complex the structure of space. Our local group is part of the Laniakea supercluster, a giant structure roughly 520 million light-years in diameter, uniting more than 100,000 galaxies. The word itself in Hawaiian means immeasurable sky. When in 2014 astronomers mapped the flow of galactic motions and defined its boundaries, it became clear that we are part of one of the arms of a colossal cosmic organism. And Laniakea is only one of many such structures. At the scale of hundreds of millions of light-years, the universe looks like a cosmic web. Filaments of galaxies and hot gas stretch across all of space. At the intersections of filaments, dense nodes, galaxy clusters. Between the filaments, voids, volumes almost completely devoid of galaxies. The density of galaxies in voids is 10 or more times below the universal average. The first indication of the existence of such superscale structures was obtained as far back as the work of William and John Herschel, who noticed the uneven distribution of nebulae across the sky. In the 20th century, the capabilities of observational astronomy grew sharply, and the picture began to clarify. Isolated galaxies turned out to be rare. Galaxies cluster into groups. Groups join into clusters. Clusters assemble into superclusters. Superclusters align into filaments and walls. The CFA2 Great Wall, one of the first superscale structures discovered, consisting of about 1,000 galaxies and stretching approximately 500 million light-years with a thickness of only 15 million. The Hercules Corona Borealis Great Wall, the largest known structure, more than 10 billion light-years in length. This is about 10% of the diameter of the observable universe. The existence of such structures poses serious questions for theorists. Standard cosmological models predict that on scales greater than a few 100 million light-years, the universe should be homogeneous. The Hercules Corona Borealis wall exceeds this limit 30-fold. Either our models are incomplete, or something was occurring in the early universe that has not yet found an explanation. In observing clusters, the effect of gravitational lensing was discovered. Light passing through intergalactic space is bent by the action of mass that we cannot see directly. This is the mass of dark matter. It is dark matter, the invisible glue, that holds galaxy clusters together and forms the filaments of the cosmic web. Without dark matter, the large-scale structure of the universe simply could not exist. Without it, the universe would remain an unstructured cloud of diffuse matter. There is one blind spot in our picture of the universe, a band of sky along the plane of the Milky Way, the zone of avoidance. The region where our own galaxy forms a dense curtain of stars, gas, and dust through which optical telescopes see nothing. For a long time, it seemed that there were simply no galaxies there. But the explanation was far more mundane. We live inside the Milky Way and are looking through its plane, through clouds of molecular hydrogen, through curtains of interstellar dust. For optical telescopes, this is an impenetrable wall. Radio waves pass through dust clouds considerably better. The Parkes radio telescope in Australia began hearing galaxies behind the dust curtain. Then Meerkat in South Africa, with its 64 antennas, joined in infrared satellites, IRAS, WISE, Spitzer, added a second kind of vision, thermal imaging through the dust. On the horizon already looms the SKA, the Square Kilometre Array, a network of more than 100,000 antennas spread across 2 continents with a total collecting area of over 1 square kilometer. When fully operational, it will become the largest radio observatory in history. Beyond the dust curtain, they found not emptiness. Galaxies were found there, more than 1,000 previously unknown systems hidden directly behind the luminous curtain of the Milky Way. They were always there. We simply could not see them. And when scientists began analyzing their redshifts and directions of motion, something unexpected became clear. Behind the curtain, the powerful gravitational attractor was hidden, a region of mass concentration drawing all the surrounding space toward it. It was named the Great Attractor. Our Milky Way is moving toward it at a speed of about 600 kilometers per second, and Andromeda, and most of the galaxies of Laniakea. We are all drawn towards something that for a long time was invisible, like an invisible stone on a stretched sheet, toward which all the folds converge. The Great Attractor, as it turned out, is only part of an even larger structure. Beyond it lies the Shapley supercluster, one of the densest regions of the nearby universe, thousands of galaxies united in an extended structure. The interaction of their gravitational fields forms the flow into which our galaxy is also caught. It was precisely the decoding of these flows that gave us an understanding of the structure of the nearby universe. What had previously seemed like a chaos of random motions turned out to be a well-organized drift toward gravitational centers. When you have a map, you understand not only where things are, but why everything moves the way it does. In July 2023, the Euclid Space Telescope was launched from Cape Canaveral, a project of the European Space Agency. Its goal, to compile a three-dimensional map of the universe covering more than a third of the celestial sphere. But this is not simply a geographical atlas. Euclid is being built primarily to understand the nature of dark matter and dark energy. After 4 weeks of transit, the telescope reached its working orbit near the Lagrange point L2. It is equipped with a nearly 1.5 meter mirror, a 600 megapixel VIS camera, and the NISP infrared spectrometer. The first full scientific images were transmitted in November 2023. One of them showed the Perseus galaxy cluster at a distance of 240 million light-years, more than 1,000 galaxies in a single frame. Another image, the first percent of the future map, covered an area 500 times the disk of the Moon in the sky and contained data on 14 million galaxies. By 2030, Euclid will have observed about 8 billion galaxies. When light from them passes near concentrations of dark matter, it is slightly bent, the effect of gravitational lensing. By analyzing these distortions for millions of galaxies, astronomers reconstruct the three-dimensional distribution of dark matter across the entire observable volume of the universe. Dark matter, 85% of all the mass in the universe. It does not shine, does not reflect light, does not absorb it. Its gravitational influence permeates everything. The rotation curves of galaxies, the speed of stars at different distances from the center, remain flat where they should be falling. This means mass is present even in the outer regions where there is neither gas nor stars. An invisible halo of dark matter encompasses the entire galaxy. What it is made of is one of the central open questions of modern physics. Several decades of experiments at colliders and with direct detectors have yielded no answer. Dark energy is different. About 70% of the content of the universe consists of something causing space to expand with acceleration. When in 1998, several independent groups of astronomers recorded this acceleration, the physics community was shaken. It had been expected that the expansion of the universe was slowing under the action of gravity. Everything turned out to be the opposite. Something counteracts gravity at the scale of the entire universe. This is called dark energy. Its nature is unknown. The Euclid telescope is designed to determine how it behaved in different epochs, and thereby narrow down the range of possible explanations. Simultaneously, the James Webb Space Telescope is building its own map, The Cosmos Web project created a catalog of about 800,000 galaxies, covering roughly 98% of cosmic history. The first results left theorists perplexed. Where a few thousand early galaxies had been expected, Webb found 10 times as many. Some of them were unusually massive and mature for their age. Standard models did not predict such a rate of star formation in the first hundreds of millions of years. Our understanding of the early universe may be in need of revision. These discoveries bring us back to the very beginning. How did galaxies form? The answer begins with the Big Bang. In the first instance, the universe was hot, dense, and nearly uniform. Nearly, but not entirely. In the primordial plasma, there existed tiny fluctuations in density, quantum accidents magnified to cosmic scales in the first fractions of a second. These inhomogeneities were imprinted in the cosmic microwave background, the faint glow left over from the era of recombination, when 380,000 years after the Big Bang the universe had cooled sufficiently for the first hydrogen atoms to form. After this came the Dark Ages, literally dark. There were no stars, no sources of light, only slowly cooling gas and dark matter, quietly drawing it into the first gravitational traps. Its clumps began to condense even before ordinary gas had cooled sufficiently. Thus, dark halos formed gravitational wells into which gas then flowed. In these wells, the gas cooled, densified, fragmented, and in the densest clumps, the first stars ignited. The first stars were monsters in scale, 100, 200, sometimes 300 times more massive than our Sun. They burned out in a few million years and died in supernova explosions, scattering heavy elements across space, carbon, oxygen, iron. Their death became the building material for the next generation. Life is literally the dust of dead stars. The first clusters of stars began attracting one another, colliding, merging. This process, hierarchical assembly, is the backbone of the modern theory of galactic evolution. Small systems unite into larger ones. Larger ones absorb smaller neighbors. Collisions trigger new waves of star formation. If in the merger process the rotation of the system was preserved and gas settled evenly into a flat disk, a spiral galaxy formed. If several large systems collided chaotically, an elliptical galaxy without disk or arms arose. The central black hole regulated this process. When it was actively consuming matter, it ejected flows of energy that heated and expelled gas, slowing star formation. When it quieted, the gas cooled and contracted again, giving rise to new stars. This is a finely tuned feedback mechanism that determines the pace and character of the entire galaxy's evolution. Observations by the James Webb Space Telescope provided direct evidence of this mechanism. A massive galaxy more than 11 billion light-years away turned out to be almost completely devoid of cold gas. The cause, the black hole at its center, was ejecting flows of hot gas at a speed of about 1,000 kilometers per second, literally washing out the building material. Despite a colossal stellar mass of 160 billion solar masses, star formation in it had been frozen at early stages. The galaxy aged ahead of its time. Over time, through tens and hundreds of billions of years, the gas in galaxies will be exhausted. Stars will cease to be born. Those that exist will go out one by one. Red dwarfs will last the longest, hundreds of trillions of years, but even they will eventually go out. The galaxy will become a graveyard of dead stars, neutron remnants and black holes, slowly dispersing into expanding space. Such is the cycle. Birth from the chaos of primordial fluctuations, growth through mergers and stellar bursts, slow fading, dissolution into space that continues to expand. Galaxies are not eternal. The universe is not static. Everything we see is a freeze frame in the longest process ever to have unfolded. We look at light that traveled toward us for billions of years. We see the past, the present in these distant galaxies is inaccessible to us, and this in itself is remarkable. And yet, it is precisely we, for the first time in the entire history of the universe, who have learned to read this past. Telescope by telescope, spectrum by spectrum, we found thousands of galaxies in a zone we considered empty. We mapped invisible dark matter through the distortions of light. We heard the motion of galaxies and understood that all of them are drifting toward common gravitational centers. We reconstructed the history of the universe from the first stars to the present day. And each time it seemed the picture was coming together. The universe turned a new page, posed a new question, showed that beyond the horizon of the known, even more of the unknown lies hidden. This is what makes galaxies not merely objects of study. It makes them a mirror in which we see the scale of our own curiosity and our own ignorance. We know a great deal, we do not know incomparably more, but we keep looking.